Hi, my name is Christian.
Hi, I'm Shadrach, and we are here to present on sustainable decentralized wastewater treatment plant for irrigation EDC 2022.
With the current increase in global temperatures leading to the drying up of our water bodies in most developing countries, especially on the African continent, and with the increase in freshwater scarcity, my team and I decided to design a system whereby local farmers can use a system used by local farmers to treat wastewater, especially greywater. The design starts with a preliminary stage whereby we have a bar screen and then a discharge channel through which wastewater, specifically greywater, will flow through. The bar screen is responsible for the removal of large amounts of coarse materials that may be present in the wastewater. Effluent from the discharge channel flows into an ABR, that is an anaerobic baffled reactor. The anaerobic baffled reactor is made up of three parts or three chambers. The first being the settler, the second being the first outflow chamber, which is responsible for microfiltration, and then the second outflow chamber responsible for microfiltration. In the settler, we are actually expecting sedimentation to happen. We designed a sedimentation pipe through which that can enhance the amount of sedimentation that goes on in the settler. In the sedimentation pipe, we've designed ridges against the internal portion of the sedimentation pipe. We expect that as the water flows over these ridges, the velocity of the wastewater with the particulates within it will reduce drastically, so that by the time it gets to the bottom of the settler, the particulates will be able to settle. In the first outflow chamber, we expect that the wastewater that came through the settler will actually pass through granular beds that have been designed for microfiltration. The wastewater from that area also enters the second outflow chamber, whereby we have microfiltration occurring over there also. The effluent from the whole area enters the TDS reactor, also called the total dissolved solid reactor. The TDS reactor is actually the last purification stage of this design. The TDS reactor is the final purification stage for our wastewater treatment system. It takes in effluent from the area and mixes it with coagulants and flocculants in the reagent tank. Inside the TDS reactor, we designed an agitator drive that is made up of the motor, a gear housing, a gearing system, and then agitator blades. We expect that the mixture from the coagulants, flocculants, and then the wastewater effluent itself will form substrates on the granular bed, ensuring that wastewater or purified water from this mixture is sipped through the granular bed into the lower base of the TDS reactor. From the lower base of the TDS reactor, water then flows through the discharge pipe into the storage tank or storage reservoir, where it is kept for later irrigation or later use. The project relied heavily on the capabilities of Fusion 360, a CAD, CAM, and CAE collaborative tool that helped us bring our design from concept and hopefully through to manufacture. With skills earned from the Autodesk CAD, CAM, CAE for mechanical engineering, and the CAD and digital manufacturing specialization offered on Coursera, tutored by Autodesk themselves, we were able to justify our product and whole system lifecycle management strategies, which include assemblies, sustainability, lightweighting, design for reuse and recycling, and many others. For our Fusion 360 design workflow, the design workspace allowed us to create parametric models of most of our components, including the ABR, the TDS reactor, the storage tank, the screens, and many other components that we use in our design. The animation help space allowed us to replicate mechanical motion using as-low joints motion. In the assembly workspace, we are able to use assembly visualization tools like the components color cycle toggle that enabled us to separate components whilst animating the design. The simulation workflow allowed us to ensure our design integrity by using real-world loading conditions on the components that we simulated. The rendering workflow allowed us to create photorealistic renderings of our models that helps us to use for presentations such as these.
Our project helps to develop global marketable engineering design skills, stimulate interest in identifying local problems, develop excellent problem-solving presentation skills. Another unique feature of our project is it helps to address SDG Goal 6, which is to provide clean water and sanitation.
In conclusion, the PPGS philosophy of S2P Africa enables the team to create a product that can be used by local farmers to serve their irrigation needs, as well as construct a framework future centralized systems can be built upon.